In this presentation, we're going to go over a new decision-making technique called goal programming. Goal programming is basically a linear programming formulation. So what that means is that in order to formulate a goal programming solution to a problem, you need to establish what are the decision variables, set your objective function as a linear function of those decision variables, and a set of linear constraints as well. Now, when we talk about linear programming, we usually talk about optimizing single performance measures. So for example, you want to develop a linear programming formulation to a problem that wants to minimize costs or maximize some profit value. Okay, so what this technique, the goal programming technique, allows is to deal better when you have multiple objectives. Okay, and we'll talk about that more in depth throughout the presentation, but basically there are some solutions where you want to maximize return and minimize risk. These are conflicting objectives, or you want to maximize profit and minimize some cost parameter. These are conflicting objectives, and this topic, this goal programming technique, allows or helps you to deal with such types of problems. The agenda for this presentation is basically a brief review of linear programming, since the technique is based on linear programming, and then we go over an introduction to goal programming through an example. So linear programming is a mathematical programming technique, and is used to solve mainly single objective problems that are under certainty. Okay, so there are no probabilities included in here. So any coefficient of an objective function, that means, for example, a cost for a decision variable, it's known, you're certain about its value. Okay, so if I want to say that a unit of raw material costs $10, well, that's what we mean. There's no uncertainty about that parameter. We're assuming that it's $10. Okay, 100% sure that it's $10. There are various types of linear programming solutions. We have linear programming solutions for transportation problems. An example there would be to minimize waiting times of cars in an intersection, for example. We have blending problems and so forth. And what we're doing with linear programming is that it's an optimization technique that has a linear objective function and a set of linear constraints as well. So here are some of the reasons on why it's important to understand linear programming. First of all, if formulated correctly, you can find an optimal solution to a given problem if the solution exists. Okay. Also, it can be easily solved using various software tools such as Microsoft Excel, which everyone uses pretty much on a daily basis. And also, there are various decision-making techniques that are based on linear programming. So understanding linear programming provides a strong foundation to understanding new decision-making techniques. Okay, so for example, we see data envelopment analysis. This is sort of like a decision-making technique because it allows you to do to evaluate relative efficiencies of different units. Okay. Another technique that is based on linear programming is one we're going to talk about today, goal programming. And goal programming is based on linear programming and allows you to find an optimal solution considering more than one objective. Okay, so let's learn the basics of goal programming through an example. And what we're going to do here is pretty much set up an LP formulation for this problem, the Burnett goal programming problem. And from there, jump into the goal programming formulation, because it makes it easier to understand what goal programming is and how to formulate these goal programming solutions by looking at the LP formulation. Okay? It also shows why is it that it is important to understand goal programming. So this company, this agency, the Leon Burnett Advertising Agency, is trying to determine a TV advertising schedule for this auto company called Chrysler. Okay? This Chrysler company has 3 goals. Goal number 1 is that ads should be seen by at least 40 million high-income men. Okay? Goal number 2 is that the ads should be seen by at least 60 million low-income people. And the third goal is that the ads should be seen by at least 35 million high-income women. Okay? Leon Burnett can purchase 2 types of ads, those that are shown during football games and those that can be seen only during soap operas. At most, there are $600,000 that can be spent on ads. Notice that this is pretty, this can be looked as what's called a hard requirement. You don't have more than $600,000. These here are specified as goals, and this play a big role when we're dealing with the goal programming formulation. However, in linear programming, this will be set as hard constraints as well. Okay. The advertising costs and potential audiences of a 1-minute ad of each type are shown in the table below. So what this table is saying is that a 1-minute ad shown during a football game is suspected to be seen by 7 million high-income men, 10 million low-income people, and 5 million high-income women. Okay, and that 1-minute ad is going to cost $100,000. Okay, same thing. A 1-minute ad during a soap opera is suspected to be seen by 3 million high-income men, 5 million low-income people, and 4 million high-income women. And that 1-minute ad, it's going to cost $60,000. Okay. Leon Burnett must determine how many football ads and soap opera ads to purchase for this auto company, Chrysler. Okay, so what is the objective of this problem? Not the objective function. So let's start with understanding what is it that the problem is asking us to do. Yeah, and the objective is to determine how many football ads and soap opera ads to purchase. So this is important because it helps us to start thinking about the decision variables of this problem. So notice that this 600,000 budget is not specified as a goal. Okay, and again, this is going to be more important. It's going to be more apparent when we talk about the goal programming formulation. But what this is saying, when we mean goals, and this is jumping a little bit ahead of goal programming, these are things that will be okay, I guess, if they're violated. We prefer not to deviate from any of these goals, but we can live with these violations. However, this specifies a hard constraint. This is something that must be met. Okay, so this is the distinction between what's a hard constraint and a goal. So let's formally define what is a hard and soft constraint. Okay? A hard constraint is one that cannot be violated. So for example, you're running a corporation and a specific project has only 1,566 labor hours available. You don't have more personnel, so you need to find a solution for this particular problem that does not use more than 1,566 labor hours, because that's you don't have any more hours. Okay? Another example will be if you're going with a budget of $850,000 on available projects. Well, you need to find whatever solution will be the optimal and will be within that amount of money. You cannot go over $850,000. Okay, so these are hard constraints. Now, sometimes these hard constraints are too restrictive. And I'll give you an example. Maybe when you're thinking about buying a car, you have a maximum price in mind. Okay, so you will not like to deviate from this maximum price or this target price or this goal price, but you may be okay if you do. Okay, so these types of constraints, because these are constraints, are called soft constraints. Okay, because they represent more goals than actual hard constraints, hard requirements. Okay, so if you have an idea in your mind that you don't want to go over $20,000 to buy a car, maybe when you go and see cars, maybe you find one that is $21,000 and you really like this car. So you're deviating from your initial goal, which was $20,000. However, you may end up making a decision to violate this goal, and in which case what we'll want to do is minimize deviation from our goals. So going back to our problem, what are the decision variables? Recall that the objective here was how many football ads and soap opera ads to purchase. Okay, so let's assume here that we define the decision variables this way. Okay, let x1 equal the number of minutes of ads shown during football games, and x2 equal to the number of minutes of ads shown during soap operas. Now, with this definition of our decision variables, we can go ahead and set up our objective function and the constraints. Okay, so let's say that the objective in this problem is to minimize the number of minutes shown during football games or during soap operas altogether. Okay, you could have easily set it up such that you want to minimize costs, in which case will be 100x1 plus 60x2. That can be the case, but in order to show the formulation for goal programming, let's just say that we set it such as the objective here is to minimize the total number of ads in order to meet these constraints. So cost, in this sense, we're going to be using it as a constraint because we have a budget of $600,000 that we cannot go over. Okay, so that's why we're setting this as a constraint here. So our objective is going to be to minimize total number of ads of minutes used for ads, and using this as constraints. So you have your high income men constraint, so it must be seen by 40 million high income men, 60 million low income people, and 35 million high income women. Okay, so it must be seen by at least. That's why we see this greater than or equal constraints. And the total budget must not exceed $600,000. And of course, we have our non-negativity constraints. Now, this is a two-variable problem, so we can solve this graphically. So let's look at the graphical solution to this problem so that we can start thinking about a goal programming formulation for this. So if you recall, when you're doing a graphical solution to a two-variable problem, basically what you're doing is modeling lines for each of the constraints. Okay, so each constraint is a linear function. Okay, so we're modeling, graphically plotting these constraints as linear functions. Okay, and eventually we test for 0, 0 in each of the constraints, and we find out what is the direction of feasibility. Okay, so that, for example, in this constraint, this is the high income man constraint. Every point to the right of this constraint, following this arrow, will satisfy that constraint. So to the left of that constraint, it doesn't satisfy the constraint. It's not a feasible solution. Okay, so what is this saying pretty much? If you're looking at these constraints, or if we're looking at the direction of feasibility. Well, if we look at the high income man constraint, direction of feasibility is to the right. If we look at this constraint, direction of feasibility is to the right as well. If we look at this constraint in this area, direction of feasibility is to the left, and the direction of feasibility to this high income woman is to the right. Okay, so pretty much what this is saying is that there's no feasible solution that meets all of the constraints or all of the goals in this problem, okay, because of this constraint. Okay, so there's this area in here that is going to be unfeasible. Okay, so one thing you can do this constraint is to relax the constraint. So for example, this constraint that we're not able to meet is the budget constraint. So you can relax the constraint in a way so that we can move it somewhere on this area. Okay, so that budget constraint stated that your solution cannot go over $600,000. So by relaxing, we can just say I cannot go over some higher amount, $800,000 or something like that. Okay, if you do something like that, this constraint is going to be moved towards the right, and then you can possibly find a feasible solution to this problem. Okay, another thing that we can do is trying to minimize deviation from goals. Okay, in order to do that, for each goal, we need to identify a cost of not meeting the goal or a penalty. Okay, so this cost is a penalty per unit short of meeting a goal. And if you set it up like this, you are doing what is called goal programming. Okay? So the idea in goal programming is to minimize deviations from goals, and it specifically deals with problems such as these ones where you don't have a feasible solution. Okay? So sometimes you're dealing with so many constraints that it's really hard or impossible to find a feasible solution to a problem. In problems such as those, goal programming is a good solution approach. Okay, so let's continue with our example to describe goal programming. So we need to specify penalties. So let's assume the following penalties. Each million exposures by which the company falls short of the high income man goal costs the company a $200,000 penalty because of lost sales. Okay? Each million exposures by which Chrysler falls short of the low income people goal costs Chrysler a $100,000 penalty. And each million exposures by which Chrysler falls short of the high-income woman goal costs Chrysler a $50,000 penalty because of lost sales. Notice that what these penalties are saying, for example, is that the high-income man goal is twice as important as the low-income people goal. Okay, and this high-income man goal is 4 times as important as this goal of high-income woman. Okay, so here we have a pretty specific idea about relative importance of goals. Okay, so what if you want to emphasize on meeting goal number 1 before any other goal, and then meeting goal number 2 before the other goals, etc. If you want to do something like that, what you want to do is add penalties in such a way that the penalty for goal number 1 it's much bigger. Okay, and this is a little bit fussy, but we'll talk about that in the next few slides. But basically, the penalty for goal number 1 is much bigger than that of goal number 2, and then the penalty for goal number 2 is much bigger than that of goal number 3, and so forth. Okay, so this is in case that you want to emphasize on meeting goal number 1 before goal number 2, and then goal number 2 before goal number 3, and so forth. Okay, and if you have a problem such as this is what's called in the literature as preemptive goal programming. Okay, but in this case we have specific penalties, relative penalties for each of the 3 different goals. Okay, so with this information, with these penalties, what we can do is formulate an LP that minimizes the cost of deviating for each of the 3 goals. And what we need to do here in order to proceed is we need to transform each inequality constraint into an equality one. So basically what we're doing is creating what are called deviational variables. Okay, so for each constraint we're going to add deviational variables, and these variables are going to assume the values that we either go over or under a goal. Okay, and these deviational variables are what's going to compose our objective function. Okay, so hopefully it's clearer, it's a lot more clear in the next few slides. Okay, but basically you develop penalties for not meeting each of the goals, and you develop what's called deviation variables. So for example, these are the deviational variables developed for this problem. Okay, so it's going to be s sub I plus or s sub I minus. Okay, and what this means is, for example, s sub I plus is the amount by which we numerically exceed the ith goal. Okay, so for each goal, let's say we have 3 goals, we're going to have 3 different si plus variables and 3 different si minus variables. Okay, so the S1 plus, for example, will be the amount by which we exceed the first goal. S2 plus is the amount by which we numerically exceed the second goal, and so forth. Okay, S sub 1 minus is the amount by which we were under the first goal, and so forth. Okay, so based on the definition of our decision variables, we can say that the deviational variables, which are assumed to be measuring millions of exposures for the first 3 constraints, can be defined as follows. Okay, so this is, remember, constraint number 1 was 7x1 plus 3x2. It's greater than or equal to 40 million. Okay, so for each constraint we develop deviational variables. So that's how we're able to remove the inequality and turn it into an equality. Okay, so our new constraint is going to be 7x1 plus 3x2 plus x sub 1 minus f sub 1 plus is equal to 40. Okay, so previously when we had the inequality here, if it was greater than or equal, if we were not able to meet that greater than or equal, we'll have an infeasible solution. Now we're always going to find a feasible solution because of these deviational variables. So if we were under this goal, what this means is that we're going to have a value associated with this x sub 1 minus parameter. So let's say, for example, a solution gave us an infeasible solution because we were not able to meet this constraint, for example. So instead of 40, we came up with 38. Okay, what we're doing now by using that equality constraint is making sure that we get a feasible solution, because now that s sub 1 minus will have a value of 2, for example. Okay, because of this equality constraint. Okay, and the same thing for the second constraint for low-income people, and the third constraint for high-income women. So let's see the final LP formulation for this problem, which is basically the goal programming formulation for this problem. So this is the goal programming formulation for this problem. Notice that our objective function here pretty much is saying that you want to minimize deviations. Okay, and each deviation from each of the goals is going to be penalized. Okay, so you're going to minimize this prioritized, if you will, set of deviations. So penalty for not meeting goal number 1 is $200,000. So for every unit that you don't meet goal number 1 is going to be penalized by $200,000. Okay. The same thing for goal number 2. Every unit that departs from the goal for that goal number 2 is going to be penalized by $100,000, and unit that's come short for meeting goal number 3 is going to be penalized by $50,000. So that's why we see these coefficients in here. Okay, notice that we have 2 deviational variables per constraint. We have that S1 minus and that S1 plus. Okay, so, and if you recall, these equality constraints were before greater than or equal constraints. So this 40, for example, this high increment constraint, the goal in here was that the solution should result in these ads being seen by more than 40,000 people. Okay, so what we want to penalize is the amount of units that we are under, okay, not over, because if the solution results in I don't know, 50,000 people, you won't have an issue with that. You only have an issue if the solution results in the ads being seen by less than that. Okay, so that's why in the objective function we are only including in here for goal number 1 that S sub 1 negative. Okay, because you're not going to penalize any S sub 1 plus. Okay, because this amount, if there's anything in here, what this is going, if there's a 10 in here, for example, S sub 1 plus, that means that the solution resulted in a really good value here for this goal, because it was seen by 50 million people instead of 40, which is good. Okay, and the same thing for goal number 2 and goal number 3. These objective function coefficients are also called the weights for each goal, and they represent priorities for each of the goals. Okay, notice that the budget constraint is not specified as a goal. That's why you don't see deviational variables in here. It was specified as a hard constraint. So let's see the optimal solution for this problem. So this is the Excel formulation for this problem. Notice that what we want to do is minimize that objective function value. Okay, so we specify here what are our changing cells. Okay, I highlighted here in yellow those changing cells that will be part of the objective function. Okay, so solver is going to find values. These are all the decision variables in the problem, but we only want to minimize an objective function composed of these 3 variables. If you remember, these are the deviations of our goals. Okay, so our changing variables are going to be this row, this complete row, the coefficient of our objective function. Like I said, we're only interested in the objective function. We're only going to include that S sub 1 minus, S sub 2 minus, and S sub 3 minus. Therefore, they have coefficients greater than 0. Everything else is just going to be 0, which means that they're not going to be included in the objective function. Okay, so the objective function, it's pretty much the sum of product of these coefficients times the ending values for these decision variables. Okay, so and then that's what this sum of product function is doing. Okay. The constraints, again, it's going to be a set of linear functions, okay, including deviational variables. So you have a 1 plus S of 1 minus. So every minus variable you have, you're going to have a 1 in there, and it's going to be a negative 1 for every variable that have an upper plus symbol in there. Okay, and this, the way you set this up in Excel, this is the sum of the products of this whole constraint. These are the coefficients of the constraints times the values for the changing cells. Okay, so this is pretty typical, and the sum of products has to be equal to the right hand side values, which is 40, 60, and 35 million people. Okay, and there are no values for deviational variables in this budget constraint because it was set up as a hard constraint. Okay, so what this is saying is 100 x1 plus 60 x2 is less than or equal to that $600,000 budget constraint. Okay. When we set that up, this is a snapshot of the solver interface. Our objective function is to minimize that L4 parameter, which is going to be that objective function in there. And our constraints are going to be the budget constraint So L11 is greater than or equal to N11. That is the budget constraint in here. This is L11, and that's N11. Okay, and the other set of constraints are the ones that include the deviation variables which correspond to our goals. Okay, so this ending value in here has got to be equal to 40. Okay, that ending value has got to be equal to 60, and that ending value has got to be equal to 35. Okay, make sure that we select the simplex LP because that's what we're using as an algorithm for a linear function to obtain an optimal solution for this linear objective function. And this is the solution to the problem. Okay, the solution turns out to be, it gives you a value of 250, but you're mainly interested in is understanding what are the values of the decision variables. Okay, so what this is pretty much saying is that the optimal solution meets goals number 1 and 2 because there are no deviational variables, so we hit our goals for goals number 1 and number 2. However, we failed to meet goal number 3, so we came 5 units short of meeting goal number 3. That's why you see some value here for that S of 3 minus. Okay? So what if the budget constraint was specified as a goal? Okay, so what if this constraint here in the bottom, you see it was not specified as a goal, so you don't have any deviation variables. But what if now you want to set it as a goal? So you may be okay with going over that $600,000. Okay. First thing that you need to do is, well, you need to add a penalty for not meeting, for a unit that you come short of meeting this goal. So let's assume a dollar penalty for each dollar by which the goal is unmet. Okay, then what we'll have is a constraint similar to this one, and what we're doing here is just adding deviational variables to that. Okay, so we added a fourth set of deviational variables, and the formulation is going to be the same, and what changes in here is the definition of that constraint. Okay, 100x1 plus 60x2 plus x4 minus x4 plus equal to $600,000. Okay, so that's going to change, that constraint, and the objective function is going to change because we need to include x4 negative as part of our objective function. Okay, so those are the two changes that you'll see. While you're reading about this topic, you may come up with the concept of preemptive goal programming. Okay, and basically in our previous example, the one we just covered, we assumed that the decision maker could exactly determine the relative importance between the goals. Okay, so for example, the high income man goal was 2 times more important than the low income people goal, and so forth. Okay, in a situation, this is not the case. Okay, so what we want to do is sometimes is to make sure that we meet goal number 1 before goal number 2, and then after we meet goal number 1, we find that we want to meet goal number 2 before goal number 3, and so forth. So what we're doing is to clearly prioritize these goals in terms of, I want to make sure that I meet goal number 1 first before I think about goals number 2, 3, and 4. And after that, I want to make sure that I meet goal number 2 before I meet goal number 3, 4, 5, and so forth. Okay, and you go in that fashion. So pretty much preemptive goal programming says that actually the way that you solve this is to just assign weights that are much bigger than other weights for other goals. Okay, so for example, the weight, which is going to be here, this is the preemptive weight for goal number 1. You have to set it in a way that is much bigger. That's what this symbol means. The weight specified for goal number 2, and the weight for goal number 2 is much bigger than that of goal number 3, and so forth. Okay, so it's a pretty logical process, and what we're doing here is to making sure that we satisfy goal number 1 as much as we can, and then for the possible, then after that we try to satisfy goal number 2 as much as we can, and so forth. Okay, and then this is just it sort of makes sense. Okay, and the term to describe this is called preemptive goal programming. So nothing really fancy in here except just the name, preemptive goal programming. Okay, so let's see the LP formulation for a preemptive goal program solution. For this problem that we were dealing, the Chrysler problem, the preemptive goal programming formulation is obtained by setting really high weights for each of the goals. Okay, so the weight specified for goal number 1 is much bigger than that specified for goal number 2. The weight specified for goal number 2 is much bigger than that specified for goal number 3, and so forth. and everything else stays the same. Okay, notice in here that this is the formulation that require that budget constraint to be a hard constraint. Right? But again, this is what's called preemptive goal programming. So if you read about that's basically what it means. Right? The general goal programming model can be formulated as follow. You have weights for each of the deviations that you want to meet, that you want to penalize. I'm sorry, and you either if it's a non-preemptive goal programming formulation, you just specifies them as a W sub I, which is the weight specified to goal number one, not meeting goal number one, and so forth. If you have a preemptive type of goal programming model, then you use that P parameter to specify a penalty that is much bigger for goal number one than it is for goal number two, and so forth. Okay, so it's pretty much what we've done through an example before, but just generalize the goal programming formulation for it. Goal programming is being used in many different areas. Okay, it's been widely applied to decision problems in business, in government, engineering organizations, nonprofit organizations, etc. Okay, these are some of the areas where you can see goal programming applications. Okay, I've seen it a lot in personal administrations, policy analysis, production scheduling, project management is being used extensively, and so forth. Okay, so this is a technique that adds value to you as a decision maker. So it's one of the tools that you want to understand. Okay, and like I said, in order to understand how to formulate goal programming solutions, you need to have a basic understanding of linear programming. So that's one of the benefits of understanding linear programming.